Okay, so in this section, we're going to take a look at something called Peterson's solution, which is going to be basically our first approach to solving that critical section problem. As a note here, Peterson's solution is just a little bit tricky and a little bit annoying, but we'll kind of go through it and get at least a feeling for some of the base ideas behind it. All right, and there will be, before you get scared off, there will be actually better ways to solve this problem later on once we get to other things like mutexes and semaphores, but for now this is kind of a more primitive way to do it. All right, so Peterson's solution is basically a way, and I'll call it also Peterson's algorithm, but what it is a way to solve the critical section problem, providing you have basically your loads and stores, right, are atomic, right? That's kind of what it's predicated on. So you have the code over on the right-hand side, right? Over here, right, basically this is written in is in terms of I have two processes, right, PI and PJ, right? So you can think of it as process 1 and process 2, right? And through this code sample on the right-hand side, you'll basically see I and J throughout. And you can imagine that code to basically run in both those processes, right? So both levels will be running, right? Both of them have critical sections, and we want to make sure, right, that this thing, right, that basically, right, we have those three conditions, right? That we have this idea, right, of it being, mutually exclusive, that's bounded waiting time, right, that's making progress, right? We want all of that, right, basically to be satisfied by this algorithm. At kind of the end of this section, right, I will talk a little bit about that, but just very briefly, it's actually complicated to show, that it satisfies those three constraints. All right, so let's try reading through this. Now, the first thing up top, right, is basically two variables. So I have my turn variable and then my flag variable. And this is what we're going to say is going to be in shared memory, right? So all my processes out there, right, my I and my J, right, both of them will have views on this, both of them can read and write from it. Okay, so we'll say that's out there, right? So basically I have that turn variable, and that turn variable, what it's going to indicate is who gets to go next, right? So does process 0 get to go, or does process 1 get to go, whatever it may be, right? So that's not too bad. Second thing over there is basically flag, right? And flag is actually an array. And that array is going to have slots for each of the processes that's running, right? So I have my two slots here, right, for basically my P0 and P1. And that, right, I'll initialize it to false. The idea there, right, is that my flag variable will be what I use, right, to indicate that somebody wants to go, right? So if process 0 wants to go, then that index 0 should be true, right? If process 1 wants to go, then index 1 should be true, right? And so I'll kind of be storing it there. So I have two things there, right? I have basically, whose turn is it to go next, and then who will I actually make go next, right? So I have my two little things there, right? And obviously those things should be in agreement, right? So in order for process 0 to run, turn should be 0. Well, in order for process 0 to run, right, turn should be 0, and then that flag of 0 should also be set to true. So two things kind of need to be true in order for me to move forward. All right, so keep that stuff in mind. Now what we have, right, is basically our main code, and this is where things get a little bit tricky. We'll go through this, but on the next slide I have an example. It's kind of worked a little bit, and it's a little bit easier to see how this works. All right, so basically I have this loop, right, because I want basically my process to run right over time and try to do their thing. Now, this code here, right, effectively is going to be the same in my process, my two processes, right? So process I, process J. Somehow, right, process I refers to like myself, right, and process J refers to the other one, right? And normally, right, I have I have the number either 0 or 1 in there, right, instead of I or J to indicate, the process number. Normally that's what would be in there, right? But here I just have the variable in there, so I can kind of think of it in terms of, I'll reuse it for different processes. The exact same code, right, is going to be running in both processes. It's just that I and J, value 0 and 1 will be flipped. So just FYI there. All right, so looking at the code, what do we have? So over here, right, basically we start by saying, okay, I'm in process I, right? I'll set flag of I equal to true. So basically what that means is I want to run, right? The process is currently running this code, wants to execute its code, right? Wants to go into its critical section. And then what I'll do, right, and this is maybe counterintuitive, is I'm going to go turn equal J. So what I'm saying is I want to go, but it's not my turn. What this is really saying is I'm going to take turns with somebody else, right? So the actual mechanism behind Peterson is to say, okay, I have two processes, I and J, and I want them ideally basically to take turns, right? Go back and forth and back and forth and back and forth. And if I do that, right, you can imagine that you do get something like progress, right? You're going to be moving forward. You do get bounded waiting time, right? You're going to constantly be switching between them. So yeah, if we just kind of toggle back and forth between them, we'll actually get that behavior that we want. So that's really what the goal is here, right? So I know it's a little counterintuitive, but we're just saying that I want to go, but I'm basically going to give the other person a chance to go first, right? And so then we'll end up alternating. Okay, so now we have a little busy waiting loop here, right? So this is going to check, while the other process is active, essentially. So you can notice here that it's looping, right? Well, flag of J is true, right? So that means that Jth process, right, the other one that's running, right? Well, that one actually, wants to do stuff, right? Well, its flag is up, and it is its turn, right? Because I just made it its turn, right? I just made J its the current turn, right? So typically I could move forward with it. So that whole loop there is basically going to wait while the other process is running, right? The other process, activated its flag. I, agreed that it was its turn to go, and so now it's running, right? And eventually it falls out, right? So either it's no longer its turn, right? It kind of relinquishes control because it's done, right? Or maybe, it's just that it's not its turn anymore, right? One of those two things happens and it drops out. Point is, when that thing drops out, right? When either of those conditions is false, that implies that the other process is no longer its critical section anymore. And so then, right, that means that it's done for a moment, right? And so that means it's safe for me, right, to jump ahead in, right, and run my critical section code, right? And that's what I'll do here, right? All of a sudden, my critical section stuff is what runs, right? Because I already know that up above, right, I set my flag to true because that means that I want to, to do something, right? And then, right, in order for that loop to exit out, probably what that means, right, is that basically it's my turn, right? It's one of the conditions, right, for that loop is that it's my turn to run. So yeah, I'll run my critical code, right? All that stuff runs, and then I'll set my flag equal to false once I'm done, right? Basically say, okay, I'm done with this stuff. Right? I can move along now, right, and let somebody else go, right? Probably what happens, right, is when I set my flag equal to false, right, that's going that's kind of on the pathway, right? Basically letting the other one run again, right? Because what happens, right, is I set my flag to false, I loop back up here, right, and I kind of get back into the mindset of, oh, I'm going to set it equal to the other person's turn, right? I'm going to set turn equal to j, right, in order to go back to the other one. And so these two things, right, basically you can imagine two processes running side by side. They're basically letting one another take a turn, right, and before they themselves go. All right, so let's take a look at a drawn-out example just to see how this looks a little bit more. So imagine I have two processes here, right? So I have my P1, my P0, and my P1. This is what I have. And let's imagine, right, that at the beginning of time, right, they both kind of start over here, right? So nothing's really run, right? Initially, right, my state of my program is this over here. Turn equals 0, flag equal false, and false, right? So initially, right, the turn variable really isn't even really initialized, right? It's not really even fair, right? It's equal to 0, right? It's whatever happens to be there, right? It's C. But our flags are false and false. So this is how it looks at the beginning of the day. Now, for now, let me just suppose I pick arbitrarily the process 0 is going to run first. So what happens? Well, let me say that basically the first 3 lines run. So I'll say this stuff here runs, right? Well, what happens? So flag 0 gets equal to true. Flag gets equal to, turn gets equal to 1, right? So basically what I'm saying is process 0 wants to run, but I'm going to let process 1 run. Process 0 want to run, but process 1 is the turn that it wants. What this is effectively saying is that process 0 wants to go, but then it's process 1's turn. And you can see that in the state over here, right? So you can see the turn is equal to 1 now. Our flag is, basically has a true in index 0 and a false still in index 1. Okay, so that's fine, right? And here, right, we're basically going to jump back and forth between executing these two processes. It's a little bit arbitrary. I kind of just picked points, right, that give us a little bit of interesting behavior. All right, so let's say we jump over to the other process, right? So we run now lines 1 to 3 in process 1. How does that end up looking? Well, flag of 1 is true, right? So now process 1 wants to go. And then I set turn equal to 0, right? So actually I'm saying, oh, it's turn 0, it's process 0's turn to go. And so I update over here. All right, turn equals 0, flag equals true and true. An interesting thing to note here, right, is that number in turn, right, it's flip-flopping back and forth, but it'll only ever have one value, right? And that one value it has is going to define who gets to go ahead and move forward, right? So it's, that's kind of who has the final say, right? At least the first time through, right? And then once they go through, then they'll try to alternate when they can. All right, so looks like, right, turn 0 ended up being, 0, well, turn ended up being 0, right? So it looks like it'll be 0, basically that P0 that gets to go. All right, so we've executed 3 lines from each. Let's say, right, that P1 wanted to run a little bit more, right? So let's say we go over here. Well, in this case, right, my flag of 0 is true, right? So if 0 wants to run, and then turn equals 0, right? So in that case, right, because there's an agreement between my flag and my turn there, right? This means that P0 should be going, and so P1 really can't do anything, right? It'll stay there in that while loop, right? And just wait, right? And not enter its critical section just yet. All right, so now we've kind of traced this bit too. Now let's jump over to process 0. So process 0's next line runs line 4. And over here, right? Well, hey, it is my turn, right? And I did want to go. In that case, right, this ends up being a loop we're going to break out of, right? Actually, excuse me. So in P0's while loop there, basically what happens is that first flag ends up being true because that second process wants to run, but that second part of that condition, right, the turn equals 0, that actually, turn equal 1, that ends up being false, right, because actually process 0's turn to go. So because I know a process 1 can't be running, right, because the turn is 0, it'll actually end up skipping over that loop, right? So that loop there, right, will basically be skipped, right, by that process 0, and it'll continue downward, okay? So it kind of continues on versus process 1 was being held there. Okay, so I've done a little bit of stuff. Now let's say I jump back to process 1. Process 1 still sees that turn is 0, still sees that that flag of process 0 is true, right? So it knows that process could be active right now. So it just sits there, right? Continues doing nothing, right? So it kind of stays here some more. Jumping over to the process 0, while process 0 got past the while loop, that means it's going to run the next line of code, that means it's going to run that printf, and it'll display the text over there, p of 0, from the critical section, right? So its critical section will run, right? And again, right, process 1 is just kind of spinning its wheels right over on the other side. Once process 0 is running its done running its code there, right, basically what happens is it sets the flag of 0 equal to false, right? So it says, I no longer want to go, right? So this over here runs. When it sets that equal to false, right, basically what happens is, this thing over here, right, that will end up being false, right? And so that loop in the other P1, right, that'll end up being false, right? It'll drop out and it'll go down and be able to run its code, right? And it's safe to do that now, right? Because we've just completed the critical section in process 0, right? So we finish up 0, right? And basically, flip-flop over, right? And let the other process go, right? So this is general process where we're going back and forth between one or another. So I know this is a little bit complicated. Kind of just get the feel, right, for the trace on the right-hand side, right, how you can basically have one of these block, right, while the other one goes. Then once it goes, it'll kind of change hands so the other one can work on stuff. So yeah, that's Peterson's solution. Oh, so just one quick note. Also in the slide deck you'll find, and in the book as well, a proof of correctness for this algorithm. And basically what it does is it shows that this algorithm, right, Peterson's algorithm, is a way, right, basically to solve that critical section problem, right? So it tries to show those three properties whole. Now for this stuff, it's a little bit more advanced than I would expect for this level of course. I would, if you have time, right, take a look at the slide here, take a look at the book, right, you can read it through it. But I'm not going to, to really require you guys, right, to study this, too much, because this is a little bit advanced. But just know, right, that it is there, right, in case you want to take a look at it.